Everybody's heard the bell. Our next speaker is going to be Sinan.
Thanks, Marie. Pleasure to be here. Thanks for inviting me. My talk is actually very similar to the last two talks in terms of the problem handled. The talk is about our work, which is, hopefully it's worth developing some scalable Monte Carlo inference for state space models. This is a joint work with Christophe and Arnaud, and a part of the reason that the talk is actually the half of the talk especially is very similar to the last one is that Arnaud Doucet is also involved in this one. Okay, here's the overview. Well, we're going to assume that we are interested in sampling from a probability distribution with density pi theta defined on some space. And as you know, most general purpose algorithms to do so require one to be able to evaluate this density for any theta, but this is not always possible. And as an example, we can show the latent variables example where pi theta is the integral of a joint density over the latent variable. And I'll denote the latent variable by x throughout the talk. Some progress has been made in recent years on this problem, mostly under the name of exact-approximate MCMC algorithms, but the solutions do not always scale with the complexity of some problems as shown in the last two talks. I'm going to also review those methods and show their disadvantages, just to make a preparation for our methodology. Okay, again, for example, if you consider the latent variables example, where pi theta is again an integral of a joint distribution with over the latent variables, if the dimension of this latent variable is actually t, and t is the size of the data, if it's proportional to t, the dimension, then we might have problems in scaling. And this talk is about how some of these algorithms can be made to scale. And our main motivation is, again, the Bayesian parameter estimation in state space models, just like the previous two talks. Okay, this is really an introduction of our notation. I'm assuming that all of you know the Metropolis Hastings algorithm. The density is pi. Our proposal density is q. Okay. Conditional on theta, I sample theta prime from q theta, the kernel, and this is the acceptance ratio, which I will denote by r theta and theta prime. Okay. And the intractable acceptance ratio problem is that being able to implement the MH update requires one to evaluate this ratio. But this ratio, in many cases, it is intractable. It's either impossible or expensive to compute. And as an example, again, if I go back to the previous slide, in such cases, you can't evaluate this integral exactly, which renders this acceptance ratio intractable. Okay. And intractability of this R acceptance ratio is the motivation for exact approximations of MCMC algorithms. We say exact because these exact approximation MCMC still target pi theta. The kernel is the kernel actually leaves pi theta invariant still. But they kind of approximate this acceptance ratio, which cannot be evaluated. Okay, there are many such algorithms, but some of them may not scale. Okay, the pseudo-marginal approach, as you saw also previously, the idea is to replace pi theta with non-negative unbiased estimators, such that the expectation of your estimator is some constant for all theta times pi of theta. Then you can actually substitute this in your acceptance ratio and get an estimate of this acceptance ratio. And if you do the acceptance rejection step properly, then you target pi theta. Okay, so this is known as the pseudo-marginal Metropolis Hastings algorithm that is proposed in 2009 by Christophe Andrieu. So these are, as I told, exact approximations of the marginal Metropolis Hastings. So you must have seen this, some of you must have seen this example from Christophe's talks. We have the latent variable example here, where we have the joint distribution pi theta and x. The marginal is the Gaussian, standard Gaussian distribution for theta. And we are assuming that we cannot evaluate this density, and we are going to do the pseudo-marginal MH algorithm with the proposal for theta being the optimal one in terms of asymptotic variance. And this Q is used to sample the latent variables. If you sample n of those latent variable, then your estimate for pi theta is this, and this is the pseudo-marginal estimate. Okay, and these pictures show that as n increases, as you invest on on the number of samples, then your algorithm actually gets better. How does it get better? Well, you can actually have a sense of that improvement here if you look at the histograms. But actually, you can mathematically show that the asymptotic variance decreases, and equivalently, the expected acceptance probability also increases. Okay. And the intuition that, with a poor estimate you get poor results is that in this denominator, if somehow you have a large estimate of your current, your current theta, large estimate of the density, then it may be hard to beat it, or vice versa. Okay, then the Markov chain becomes sticky. The reason it becomes sticky is that you keep both your theta and its estimate in your during your iteration. Okay, so if I define the integrated autocorrelation time, I should begin with the estimate posterior, the estimate of the expectation of this function f with respect to pi out of m samples is if this is this average. Okay, we know that this average is unbiased if theta 1 is from pi, and then the variance of this average is this expectation. And if you multiply this by m, and if you take the limit, that's tau, and that is your integrated autocorrelation time. Why is this important? Because if you have m samples, okay, and the variance of the average, which is an estimate of the integral of this f with respect to pi, is actually tau divided by m. So it's a good way, it's a good tool to compare algorithms with fixed budget. And another important measure for Markov chain Monte Carlo algorithm is the expected acceptance probability, which is pi d theta q theta d theta prime. You are at theta, you propose at theta prime, and this is your acceptance probability. So this integral gives the expected acceptance probability. Okay, these are equivalent measures. So as you can see, when I increase my n, the expected acceptance probability increases equivalently, which decreases the estimated autocorrelation, the integrated autocorrelation time. Okay, but what if, this actually, the message that you should take here is that the algorithm improves with capital N, right? The number of samples that you use. But what if the complexity of your problem increases with somehow increases with the data size, for example? Then I introduce this large T, okay, this capital T. So capital T is the size of your data. And our posterior distribution, our target distribution this time is the posterior distribution of theta given the observations y1 to t. So we have a prior eta theta, and this is the likelihood, okay, and y1 to t are the observations. So we are interested in this kind of, posterior distributions. We are going to assume that there exists some latent variables with which we can write this likelihood, in terms of the latent variable and observations, like that. Okay, this is the joint distribution of x1 to t and y1 to t, and its integral over x1 to t is your likelihood. Okay. Well, in most cases, unless for example, you are linear or you're Gaussian, this is hard or impossible to evaluate the likelihood function. But the joint density is relatively easy to evaluate for any x1 to t and y1 to t. Okay, so this is easy to compute, but this is not very, this is not that easy to compute. Okay, this integral, we will treat this as kind of intractable. Okay, and that's our intractable likelihood. And we will, we will consider the cases where this capital T is an issue. Okay, it's, what happens when it's large. Okay, our motivating example is state space models, or the hidden Markov model. So you have the latent variables here, x1, this is a hidden Markov process. Okay, it's a Markov chain defined by its initial density and its transition density mu and f. Fortunately, somehow we have used the same notation here for the Markov chain, and the observation densities are g. So we only have access to a process. This is the observation process here, such that the conditional upon the latent process, the observations are independent, and this is the observation density given xn of the observation yn. And theta in our setting is an unknown parameter of prior density eta theta. Okay. And again, the intractable likelihood, this time, we have an explicit expression for the joint density here. Okay, this is the joint density of the hidden Markov model, as most of you know. Okay, so the Metropolis Hastings acceptance ratio can be written as prior times the likelihood, and there's also the ratio of the proposals. And what makes this intractable is, again, as I said, the intractability of this likelihood. Okay. So the intractable quantity, as I said, is the likelihood ratio. There are effective methods to estimate this likelihood unbiasedly, and they are based on sequential Monte Carlo, or it's also known as the particle filter. Now let's see what SMC methods are about. Very briefly, sequential Monte Carlo, or the particle filter, was initially developed to recursively approximate the filtering density here, P, the posterior density of xt given y1 to t, or the whole path x1 to t given y1 to t. This time it's capital T, assuming that we have observations until time capital T. And the main idea is to propagate through time a cloud of possibly weighted samples such that their empirical distribution is a good approximation of the filtering density. And a byproduct, well, which is the most important thing for us in this setting, is that there is a non-negative estimator. There is a non-negative and unbiased estimator of the likelihood, which can easily be obtained as a byproduct of the sequential Monte Carlo algorithm. So if I'll ask you to look at this picture in a colorblind way, because I'm going to use it again for conditional SMC. So this is the sequential Monte Carlo algorithm. At time 1 you have particles x1 to x5, for example. Then you resample. Some of them give birth to more than one ancestors, and it goes on like this. So how is the algorithm going exactly? You sample at time 1 from a density M. Okay, we are going to be we are going to be general, and we are going to assume these densities, these proposal densities. So the algorithm goes like you propagate particles from proposal distributions, which are at time 1 m, small m, and at time more than 1 capital M, and then you wait. Okay, you have some weights, and then you resample. And this is the resampling step, and this is the weighting step, and this is the propagation step. Okay, and an unbiased and non-negative estimator of this likelihood is the product of the average of unnormalized weights. So basically, we can run a sequential Monte Carlo, use this estimator in the Metropolis Hastings algorithm, and we have a pseudo-marginal algorithm. Okay, so the idea is again replace this with a non-negative unbiased estimator obtained from SMC, and because the expectation of this estimator is again the real likelihood value, and the pseudo-marginal MH for state space models look like this. Okay, I just changed the target density as the prior times the estimate of the likelihood, which is an estimate of the target density at time theta prime, basically. Okay, so we have a toyish example. It's a non-linear, non-Gaussian benchmark model. This is the state space model that I'm going to show the results of our experiments for. This is a very well-known state space model. Basically, it's known to be a very highly non-linear and non-Gaussian, non-linear. So the static parameter of the model is, it's a two-dimensional vector, which are the standard, which are the variances of the noises, Vt and Wt. So if I run my pseudo-marginal Metropolis algorithm to estimate those parameters and perform and measure the performance of my algorithm, the PMMH algorithm, so the marginal Metropolis Hastings, then I can measure it as I told you by using integrated autocorrelation times, and as you can see here, at capital T equals 1,000, when I have 1,000 samples, 1,000 observations, this is the integrated autocorrelation time. Okay, if I use 2,000 particles, but as T increases, capital T increases, the integrated autocorrelation time increases, and since the smaller integrated autocorrelation time, the better, we can see that our algorithms actually, the PMMH algorithm actually gets worse. But there are two alternative algorithms here which do not get worse, and I'll come to those algorithms later. Okay. Alright, so what's wrong with pseudo-marginal algorithms? That has already been explained, but I like to repeat. In pseudo-marginal algorithms, one estimates this likelihood, pi theta y1 to t, and the likelihood at the proposed value independently. Okay, so you have two independent estimators whose variance actually increases with the data size. And variability of the acceptance ratio has a big impact on the performance of the algorithm, as shown by joint works of Andrieu and Christophe and Matti. So what's happening here? We are in a situation where for a fixed number of particles, the variability of the estimate increases with t, as as mentioned. So we notice that due to the independence, even as theta prime goes to theta, the variability of this ratio of estimators does not vanish. So in what follows, we motivate the need to introduce dependence between the estimates in order to ensure that as theta prime go to theta actually, which is the case as your data increases, because as your data increases, you know that your posterior gets more concentrated. So you tend to take smaller steps, right? As you tend to take smaller steps, then it actually is the case that this theta prime goes to theta. We then explain how to estimate this ratio of likelihoods directly and design a correct algorithm. This is just the motivation part, so we want to simplify the discussion and consider the scenario where the likelihood is a product of the densities of the observations. So the observations are IID, so that the likelihood can be written as a product like this. And if I denote by P0 the actual distribution of the observations, actually you can say that if the model is identifiable, then we have that this logarithm of the ratio tends either to minus infinity or plus infinity. Okay, it diverges. As a result, the Metropolis Hastings acceptance ratio vanishes or diverges to infinity. So if you fix theta and theta prime, and if you increase t, okay, that's what happens. But actually, this is not the real picture. This is not a very accurate, explanation of what happens in the Metropolis Hastings algorithm. Because in the Metropolis Hastings algorithm, if you really want to have a good algorithm that mixes well, you don't fix the the average distance between theta and theta prime as t increases. You tend to make it smaller. So that's why we are on this slide we are looking at a slightly different thing. If theta prime is theta plus epsilon divided by the square root of t for some epsilon, okay, and this is the case in random walk Metropolis Hastings algorithm. Under some regularity conditions, we have this expansion. So what is important here is that this is a constant. This will vanish. And we expect to have, therefore, a central limit theorem for the expression on the right-hand side. Okay, this motivates us to estimate the ratio directly and design a correct algorithm, as I told before. And the above analysis cannot be exploited if we use independent estimators for pi theta y1 to t and pi theta prime y1 to t. Okay, that's why there is the need of some correlation, and actually Arnaud's method is is just addressing that as well as Monte's the method that Monte presented. So the shorthand notation, I don't want to clutter the pages with 1 to t, 1 to t. So let x be x1 to t and y be y1 to t. A classical way of estimating the likelihood ratio uses the identity, this identity, okay? So basically our motivation here, I hope it is clear by now, we want to estimate the ratio instead of the numerator and the denominator separately. So how can we estimate this ratio? Well, we can exploit this relation. Okay, what does it say? It's this ratio of unnormalized densities with respect to the posterior distribution at theta. So assuming if we could sample from this posterior distribution x given y, and remember x is actually x1 to capital T and y is actually y1 to capital T, right? Then actually the expectation of this ratio here, when x is distributed according to the posterior distribution at theta, is really the ratio that we are looking for. Well, okay, of course sampling from this exactly is an issue, but we could design an algorithm targeting the joint distribution. Okay, that gives that idea. So we have the joint distribution here whose marginal is really pi theta, which is the posterior distribution of theta given the observations y1 to t. But we have a joint distribution, okay, instead that we are going to target. But since the marginal is the same as our target distribution, we are fine. So as I said, we target the joint distribution of theta and x given the observations, and one can show the reversibility of this algorithm. So what does this algorithm do? We are given a theta and x. You know, a one-step update is that we sample theta prime from this Q, and with probability, this ratio, we either accept theta prime and stick to x, or otherwise we stick to theta and x. So, okay, this is good, but this doesn't update x, of course, right? This only updates theta. But this just exploits the fact that this x is distributed according to the posterior distribution of theta pi theta x given y, okay? Because we are now targeting joint distribution. To show the reversibility, of course, you assume that this x comes from pi theta x given y. So x is not updated, and we must combine this with an update of x, okay? Therefore, you have the Metropolis within P-Gibbs ideas, for example, as shown as Linston in 2015. Okay, and for potential improvement on this, we can exploit the continuity of pi theta x1, x and y in theta. And how is that? Well, we can actually write. We can use this, a variance reduction technique already known in the literature and proposed by several people, including these references here. Okay, so if you do a two-step, variance reduction technique, that is p theta prime y divided by p theta y can be written as the product of two ratios by using a different another theta value, which is theta tilde. So you can basically factorize this ratio as a product of two ratios. Okay. So what you do here, that you already have a sample, in your MCMC algorithm, you already have a sample from the posterior distribution at theta. What you have to do is you sample this x prime from pi p tilde theta tilde given, p theta tilde x given y. Okay, so that's what this algorithm does. Given theta and x, we sample a theta prime. This is the same step, and then theta tilde is the value between theta and theta prime, and we sample x prime from the posterior distribution at theta tilde, and with probability that is indicated in this expression, we accept or reject. Okay, so what makes this algorithm not implementable? Well, again, this exact sample. We need this exact sample in order to implement this algorithm, otherwise this is a good algorithm. But actually, you can write the right-hand side of this expression by not using an exact, by not using the exact posterior, but a kernel that leaves this exact posterior invariant. So what do I mean? I mean this one. So again, the left-hand side, I'm trying to do the same thing, but this time by using a kernel which leaves the posterior at theta tilde invariant. Okay, it's not easy to sample exactly from this distribution, the posterior, in a hidden Markov model, but it may be easy to sample from an invariant kernel. From a kernel that leaves that posterior distribution invariant. And if we further have reversibility, if this kernel is actually reversible, then actually we have an algorithm that we can implement. So the following is a valid algorithm for the joint distribution, and it is basically a version of the dragging fast variables algorithm of Neal in 2004. So this we call as annealed importance sampling MCMC algorithm, AIS MCMC, but actually it's annealed importance sampling with just one step. I'll come to the generalization of that later. So you anneal with two steps only, okay? You propose theta prime and you set this theta tilde, the middle value. You can actually do any other value as well. It is still valid, but it makes sense somehow to take the average of these two. And you sample x prime from a kernel that leaves pi tilde theta tilde, p theta tilde x given y invariant. Okay, the posterior distribution at theta tilde invariant. So with probability this, which you can perfectly compute, you accept or you reject. So the question is here, what is a good candidate for this kernel? Okay, again, this kernel is the posterior distribution of x given y at parameter theta tilde. Before going to that, as I promised, this is the generalization. So we can actually do this annealing, of course, with more steps. Okay, it's possible to generalize this and introduce k greater than 1 intermediate steps. For example, if you consider these intermediate distributions such that they are between pi theta x given y and pi theta prime x given y, and they are known up to normalizing unknown normalizing constants, and this is the annealing schedule that you have. You may have something else. And if you also consider the associated Markov kernels, again, this r theta theta prime k leaves pi theta theta prime k invariant. Then, in this case, you sample x1 from, I'm sorry, this must be k equals 1, of course. x1 from r theta theta prime 1, and xk from r theta theta prime k, condition on xk1, and you compute this ratio in the acceptance ratio. Okay, so it's a simple extension once you understand the previous algorithm with only one intermediate step. Okay, and with some conditions on these intermediate distributions and the kernels, such as ergodicity of these kernels, for example, the estimator can be shown to be consistent. Our candidate, this is the crucial part in terms of implementation of this approach. Our candidate is the conditional sequential Monte Carlo algorithm. Okay, we propose the use of that in our algorithm. Let pi theta x1 to t is the conditional distribution that I was trying to tell you, say all the time, pi theta x given y. And the conditional sequential Monte Carlo, of course, can be run for this conditional distribution. It's a particle-based algorithm, okay, and it actually implies, it actually corresponds to a Markov kernel. If you think, this algorithm is conditioned on x, okay, you run it and you produce an x prime, okay. So the probability from x to x prime actually is the transition from x to x prime is a Markov kernel, is done by a Markov kernel, which I denote by r theta n. Well, this Markov kernel is pi theta invariant. Well, this result has already been shown. It was shown in 2010 in the particle MCMC paper. But in fact, and more importantly, this is pi theta reversible. Okay, remember from the previous slide, we are actually looking for a reversible kernel as well. Okay, and this was shown, for example, both versions of the conditional SMC were shown to be reversible in this recent paper. By Nicola and Samit, and it can be shown to have very good mixing properties in also recent papers. Okay, so this is the conditional sequential Monte Carlo. The reason I wanted you to look at this picture in a colorblind way was that, you know, I'm going to use it for a conditional sequential Monte Carlo for, you know, the real purpose of this picture. This is the sequential Monte Carlo. All the arrows and the values of these states are actually generated by the sequential Monte Carlo algorithm, and then you select, you know, one of the particles here, and then you go back by following the arrows in a backward way. Okay, so that's the classical conditional sequential Monte Carlo algorithm, and you actually sample from these particles according to their weights at time capital T. Okay, so again, as I said, this is the conditional sequential Monte Carlo part. Okay, the conditional particle filter that is conditional on x1 to t, and then you sample a path. You know, you sample actually kt, and then you go backwards by, again, you know, following the arrows backwards. But actually, this is not, you know, when we use this in our algorithms, we didn't get very good results, and, you know, we didn't have a, you know, a theory about that, that, you know, that is to the very point. But the reason is most probably because of the path degeneracy problem in the sequential Monte Carlo. So at time 25, 24, for example, you know, assume that capital T is 24. At time 24, you end up with only one particle for time 1. Okay, and if you follow the arrows back by only sampling at this time, and if you go back, you are actually bound to go to this particle. Okay, so the variance is very high actually. The variance of some function of x, the initial values of x with respect to the posterior is approximated with a high variance if you do that. Okay, well, there's an alternative to that. If you can compute this transition, this proposal density, there is an alternative to that, and that is proposed by Whiteley in the discussion of the particle MCMC paper, and that is conditional SMC and backward backward sampling. So in backward sampling, what you do is as follows. You generate all the variables, then you forget all the arrows. Okay, imagine you forget all the arrows here, and you resample those arrows, and then you sample 1k here and go back. Okay, so that is also valid, and that, you know, more importantly for us now is that it's also reversible. So we can fortunately use that as long as we can compute this n. Well, which in turn is equivalent to saying that if we can compute this f, because if we can't compute this f, we are kind of bound to sample from this transition density. Okay, so the same hidden Markov model, and these are our results. So as you can see, as capital T increases, the integrated autocorrelation time for those parameters in our AIS MCMC algorithm that uses conditional SMC with backward sampling actually does not increase, unlike PMMH, whose performance gets worse, as already shown in the last two talks. And this is the Metropolis within P-Gibbs algorithm of Linston et al. That was published in 2015, I guess. And that also doesn't generate, our experiments show that also doesn't degenerate, sorry. We also observed other things. For example, when we increase the budget per iteration by, for example, increasing the number of intermediate steps in our AIS MCMC algorithm, then, as you can see, the performance gets better. But you can always question, whether it is worth or not, because you're actually doubling the computation when you increase from 1 to 2. Okay, but maybe because of some convergence issues, you may prefer that. But if you invest on more particles in this Metropolis within P-Gibbs, which doesn't have an annealing, procedure inherent, then we actually observe that it doesn't get much better. Okay, it stays where it is up after a while. So it is more, our algorithm is kind of more responsive to the increased budget per iteration. It's kind of more worth doing this if you have more budget. Okay. And PMMH also gets better, but PMMH actually does have another problem, and that problem is the scalability problem. Okay. Okay, I don't have time to talk about other things, but just to tell you that, my last remark is that if you do conditional SMC without backward sampling, then the results are not that good. Okay, and that's because probably the path degeneracy issue. So if you have a hidden Markov model whose transition density cannot be written down, cannot be calculated, then probably this framework may not be preferable. Okay, I have some more slides, but maybe upon your questions I will show them. Thank you. Oh, actually, I have.
You've got another few minutes. Yeah.
Okay.
You want to carry on?
Yeah, it's probably a silly question, but if you're interested in estimating the ratio of two quantities, of two densities or normalizing constants, I mean, there are more stable solutions like, say, bridge sampling and things like that. So what is the reason for not choosing those different solutions?
Well, we could, as long as we end up in a reversible, in a valid MCMC algorithm. I didn't consider using those solutions actually, but it would be interesting to look at them and then and then decide if we keep reversibility and validity of the algorithm still.
So unbiasedness is not enough.
Sorry?
Unbiasedness is not enough.
Unbiasedness of the ratio of estimators? No, it's not enough. Actually, yeah, it's not enough. Well, it's not like the marginal MH where you have the unbiased estimator for the numerator and denominator. You have to satisfy other, another condition. You have to show that it's really reversible, basically. For example, if you did multiple conditional SMC and followed by backward sampling, and if you averaged out the estimates of those ratios, that is still an unbiased estimator. But you can show that it doesn't preserve reversibility. So it doesn't have invariant. It doesn't have pi as invariant distribution anymore. But there's a tweak to that. You can actually play around with your proposal kernels, with your MCMC kernel overall. You can be asymmetric and show that actually you can actually use averaging of acceptance ratio estimators, and you can still be reversible. I mean, but it's not directly applicable. That's what I'm saying. Actually, since I have, I guess, 2 minutes, as an answer to your question, we considered to make use of more or all possible paths from backward sampling. This is actually possible, but you need to change the algorithm a little bit. You need to basically define two Markov kernels, and you need to choose one of them with half probability and the other with another half probability, and then it works. I can show you the details if you want.
Yeah, so it's different from something like multiple importance sampling, or
yes, it's a bit different.
Okay, let's thank your speaker again.